Good evening, everyone. I'm Jeff Badnock, and on behalf of the Alumni Association Community Lecture Series, I am happy to welcome you to the fourth lecture of the 22nd Annual Community Lecture Series. We couldn't do this series without the stellar help of the Alumni Association staff. It's a wonderful organization. If you're an alum and not a member, think about joining. Anything you can do to help the Alumni Association helps the University of Montana. First, as always, please silence your phones. Don't be that person that gets a call in the middle of the lecture. This year's series is entitled Shoot the Moon, and I've been told that there's been some questions about the soundtrack that plays before the lectures. That's a soundtrack of moon-inspired music. You'll get the soundtrack, you'll get the listing of the songs and the artists before the series is over, I promise. As always, after our lecture is given, we'll have an opportunity for you, the audience, to ask the lecturer questions about the material that's been presented or anything else that falls within the purview of her expertise. When you do that, we'll have microphones that will circulate through the hall, and please wait for one of our people to bring you a microphone and speak into it directly, just as I am. It's important that we capture your question because our lectures are recorded by MCAT, and if your question isn't picked up on the microphone, it's not going to be on the video. So please make sure that you speak directly into the microphone. As always, we'll start tonight with a moon poem. This poem was written by James Joyce, a mighty, mighty man of letters who wrote Ulysses, Finnegan's Wake, Dubliners, among other things. He's not generally thought of as a poet, but he is every inch a poet. He is every inch a poet. And here's his offering tonight. Oh, and before I recite this, there were two words I had to look up because it is James Joyce. One of the words is plenilune. That means full moon. And the other one is capuchin, which is a monkey. Okay. What counsel has the hooded moon put in thy heart, my shyly sweet, of love in ancient plenilune, glory and stars beneath his feet, a sage that is but kith and kin with the comedian capuchin? Believe me rather that am wise in disregard of the divine. A glory kindles in those eyes, trembles to starlight. Mine, oh mine. No more be tears in moon or mist, for thee, sweet sentimentalist. It's my pleasure at this time to welcome tonight's lecturer, Nancy Hinman.
I have my own. I'm Nancy Hinman. I'm in the Geosciences department, and I'm actually an oceanographer. And you might be wondering what an oceanographer is doing here in Montana. It has been 150 million years or so since the oceans were here. But I have the good fortune of studying hot springs in Yellowstone, so I'm able to make up for that lack of beach and ocean. Tonight I'm going to be talking about some of my research and how it fits into the larger picture of astrobiology. Astrobiology is a fairly young field. It doesn't involve just biology, it's geology, it's physics, it's chemistry, it's mathematics, it's engineering, it's all sorts of disciplines melded into one. So in many ways, astrobiology today is reminiscent of oceanography when it was a young science. People didn't really take oceanography seriously when it was young, and as we see sciences mature, they become more mainstream. So astrobiology is a fairly young science. So I have a quote here. The probability of success is difficult to estimate, but if we never search for the chance, it's too small on my screen. The chance of success is 0. Now, this is one of the first quotes that, raised interest in exploring space. It was written by Giuseppe, I gotta read this too, Giuseppe Concini and Philip Morrison in 1959. So the inspiration for a lot of the work that we've accomplished in the nearly 60 years since then comes from their inspiration, their words to the community at the time. So there's no place like home. We're all familiar with Earth. For thousands of years, humans have thought the Earth was the center of the universe, and in general, and in particular, that humans were the center of the Earth. So understandably, our view of other worlds is clouded by our vision of our own. And so we are limited to one example. In statistics, we would say n equals 1. It is not the best situation if you're trying to look for patterns or if you're trying to look for life on other worlds. The Earth has great biodiversity. And so even though there's this mass of living organisms, the organisms on Earth all have the same common functionality. They all turn carbon dioxide into sugar. And that's how they make a living. Or as we turn sugar back into carbon dioxide. So we have carbon-based life here on Earth. And we assume that that is a fundamental property of life anywhere that we look for it. Whether that's correct or not, we won't have any way of knowing until we find other life or we are proved wrong. One has to wonder, if we are proved wrong, how will we recognize life? If it's a different system. So we look for organic carbon. The problem is that organic carbon is everywhere. It's not just on Earth. The organic carbon on Earth is very well organized into units of amino acids and proteins. It's very well organized. But there's a lot of organic matter in the solar system that is not well organized. It is much more chemically diverse than what we find here on Earth, but nevertheless, it's there. So if we were to, say, pick up the Murchison meteorite and ask the question, is there life here? And we based it solely on whether there was organic matter there or not, we would conclude that there was life on the Murchison meteorite, which we know is not true. So we have to look for other evidence. What other evidence would we accept? We look for evidence in the form of biosignatures. Now, I don't know if you've heard of biosignatures. Biomarkers are a type of biosignature. In either case, a biosignature is an object that can only be made by biological activity. So if you can make it synthetically and you can make it biologically, it is not a biosignature. So we look for biosignatures. And that, we will see, is easier described than found. The second thing I want to talk about tonight is what sort of living systems we might expect, or perhaps better stated, hope that we will find on other worlds. will we find systems of environments like our own? And when I'm talking about worlds, I'm talking about the worlds in our solar system. And so to answer that question, we need to study life on Earth and the environments in which we find it. And of course, those environments tend to be populated by more primitive life. Primitive life, more primitive than what we have in this room, for example. But even in this room, there's a whole host of very primitive organisms. Of course, you have to remember that by the time we recognize life in the geologic record, it is already highly evolved. It is no longer very primitive. Now, where we find this type of primitive life on Earth are in places that we would consider extremely inhospitable. They are too hot. They are too cold. They are too acidic. They have too much radiation. Basically, these organisms, these primitive organisms, live in environments that would hurt your hand if you put it there. And that is because those environments are the only ones available for these organisms. They can't compete. They can't compete against us. They can't compete against higher plants. All right, so where do we look for these analogs? We look for them in these extreme environments. And what will we look for when we look at other worlds in our solar system? These worlds have environments where life may have evolved, and we can only use our examples here to speculate whether we might find them there. So this evening, we're going to take a short tour of the solar system, looking for many of the traits and environments that organisms on Earth call home. So there are many definitions of life. Any biologists in the room? Perhaps. One, oh yeah, at least one. Okay, good. I'm on alert. And so there are many definitions of life. And life certainly has many capabilities. But when searching for life elsewhere, we can't be constrained by our own knowledge of life on Earth. We must also be informed by it. So we need to look for a minimalist definition. One thing is for sure, that if we do find life, I guess this is really an assumption, it will be a minimalistic type of life. Of course, I don't remember who said it, but one of the surest signs that there's intelligent life in the universe is that they haven't looked for us yet. So the minimalist definition is that life is a self-sustaining chemical system capable of Darwinian evolution. Now, the parsimony of words in that is just beautiful. But let's pick it apart and see what it actually means. First, life must be able to harness energy. The source of that energy on Earth is either sunlight or chemicals. So we would use that as a model for looking for life elsewhere. Are there chemicals? Is there sunlight? The first, photosynthesis, encompasses the process of converting non-living carbon dioxide, into living carbon that we call organic matter. And for photosynthesis, light is the source for that. Certain ranges of light have enough energy to enable this conversion, but not so much energy that it degrades the particles or the molecules shortly after they form. So we're very fortunate that we live in an environment that gets enough of that energy in that particular range. And we're also very lucky that our atmosphere has a shield for UV radiation. Okay? If we didn't have that shield, then we would likely not find life on the surface of a world or of our planet. UV, that is ultraviolet radiation, has enough energy to break apart the bonds in the organic matter. So this is really kind of an enigma, and it's one of the areas where I do some research, and many others are doing research as well. What about before Earth had such a fine shield, the ozone layer that we hear about? What was the situation like on the surface of the Earth before that ozone layer was there? Well, I'll tell you, there was an awful lot of radiation. Without our atmosphere, there was an awful lot of radiation built up. So where on Earth would life have evolved in that situation? But let's keep going. We can't answer that question, so let's keep going with our minimalist definition. The system must be self-sustaining. It cannot rely on outside templates for replication. There are templates out there, and it may well be that organic molecules attach themselves to these templates, and that then they form bonds between them, and so they are arranged and carbon bonds are propagated, and eventually organic matter is formed. But clay minerals are not alive. So life has to have a different mechanism for self-replication. So life also must have a means of isolating itself from the environment. When you wash dishes, you use, presumably, dish soap. And that dish soap can form bubbles. And those bubbles isolate the interior from the exterior. And that's what cells need to do. They need to keep all of those capabilities, energy, replication, waste removal, all of those functions that a cell must do must stay inside some container. So there has to be some way of isolating the cells, the interior of the cells, the guts, from the environment. Now, all of these characteristics are necessary. Living systems must have three characteristics that I just mentioned: the ability to harness energy, the ability to self-replicate, and the ability to isolate themselves from the environment to make that happen. But the key is those characteristics are not sufficient. Life must also be capable of adapting to changing environmental conditions. Living systems must be able to evolve in the Darwinian sense in response to environmental pressure. So if we look at our definition again, all of the parsimony of words we see up there encompasses a minimalistic definition of life. So let's look at a couple of examples for evidence of life. The first topic we're going to cover. Now, it's not in its normal habitat, but we easily recognize this as evidence of life. We know a lot more now about dinosaurs than we did 50, 100, 200 years ago. But humans recognized bones as fossils as soon as we saw them. They might have been a little bigger than we expected, because we don't see animals this big. But we recognize them as bones nonetheless. This image here shows not only our dinosaur, but it also shows a mammoth skull back here as well. And then there's an example over here that I can't quite make out. But there are many different shapes and sizes of organisms in life. what about a less obvious example? Behind the dinosaur in the previous picture, and shown here, is a microbial community that is less recognizable as a fossil. Now, I don't know if you would go walking through the woods and come across a nice outcrop of this, which, if you're a geologist, would immediately, that would be the end of your hike. You would be looking at this. This is not, this is evidence of life, but it's not easily recognizable evidence of life. It's not an individual fossil. This is a fossilized community of single-celled dinosaurs that thrived over 3 billion years ago. Yeah, sure, the rock is a little mangled. It's a little harder to imagine what it looked like originally. You know, but a little mangling can't hide what the fundamental characteristics of this rock are. These layers, if we straighten them out and stretch them out and lay them flat on the seafloor, are the environment in which these rocks formed and these organisms lived. This fossilized system is sort of loosely termed a stromatolite. Now, there's probably a geologist or two out there. I have to tell you that geologists tend to be a little picky about the terminology. So on the off chance that there is one in the audience, this might more accurately be called a microbiolitic chert. There'll be a quiz later. Anyway, these are layers upon layers of the mineral quartz, common mineral, and the remnants of thin microbial communities called biofilms. Over 3 billion years old in Australia. Now let's venture even a little farther afoot. Let's look at something that is even harder to recognize as evidence of life. In fact, you can't see these unless you have special instruments and special laboratories to look at these different carbons. Isotopes, these are carbon isotopes, offer another way to look for evidence, another way to look for biosignatures. Now we know that different elements have different numbers of protons and neutrons. The proton define the element. So here, for example, 6 protons, they're in red, define, are they in red? 1, 2, 3, 4, 5, 6. Nope, they're in blue, sorry. The 6 protons define this atom as carbon because the atomic number of carbon is 6. And then carbon-12 has 6 neutrons for a total mass of 12. That is the most abundant form of carbon. And it is also the lightest form of carbon. So I look out there, I might see an occasional white eyeball here at the moment. Just stick with me here for a second. We call this carbon-12, and it's the lighter of the 2 stable isotopes. The other is carbon-13 on the right, which has 1 more neutron. Carbon makes up the bulk of organic matter, and life tends to incorporate the lighter one into its structures. Simply put, life is lazy. It takes more energy to push around the heavier one than it does the lighter one. So life tends to use the lighter one instead. Okay, now I think that this is the only data figure I have in here. So stick with me here. This is a diagram that shows us the carbon-13 signature relative to the standard, okay, which happens to be PDB, and in parts per thousand or parts per mil. Okay, so here's 0. All right, PDB happens to be a marine limestone, so that's why marine limestone here is centered around 0. Carbon-bearing substances that have more carbon-13 tend to be, or are on this side, they're considered heavy. Okay? Carbon-bearing substances that have more carbon-12 are on the negative side. Now let me point out a couple of things here. Up here at the top is atmospheric carbon. So atmospheric carbon is a little bit lighter than the standard. Freshwater carbonates, groundwater inorganic carbon. Let's see, what else do I want to say here? These organic matters are lighter than our standard, but they're not as light as these organic materials, plants, soil carbon dioxide. Look at this. Biogenic methane is extremely light carbon. Okay? And coal and petroleum, which we know comes from biological systems, is also fairly light. So we can take a rock, like the Kitty's church that we just saw, and we can analyze it. We can analyze it for carbon isotopes. And if they're light, then we have a piece of evidence that we can use to say that that formed from a living system. Well, we're not going anywhere. Ah, there we go. Okay. I have to make an adjustment to my screen here. Sorry about that. But then there's nothing that's easy. Right? We have to consider what happens to the rocks afterwards. Soft sediments, such as those that we find the dinosaur bones in, harden and turn into rock. Those rocks are buried. Those rocks experience changes in temperature and pressure, or they might be exposed to fluids that are incompatible with the minerals in the rock. And that changes the rock itself, and it changes the biosignatures that we find there. If we have to understand these processes well enough to backtrack through those changes to the original signal. There's a whole field that looks at those processes. That's called taphonomy. And the best description of taphonomy that I've ever heard is, it's everything that happens between death and discovery. That pretty much covers it. But at some point you have to recognize we can't pull all of that information out of the rocks yet. So there's some ambiguity here. It's, in some ways, seems more like a game of chance than it does a logical sequence of discoveries. The goal of this research, including my own, is to separate signatures that are abiotic from those that are biological. And in doing this, we expect to better distinguish those two types of materials in the geologic record. The abiotic ones from the biological ones. Well, you know, we have enough trouble with our own planet, as you've seen. We look at rocks that we don't recognize as fossils, and some that we do. But at least we can say it's habitable. So we need to use habitable environments as analogs for possible environments that we might find on other worlds. Now, life on Earth can survive in a wide range of chemical and physical conditions. We can only survive in a limited temperature range, a limited range in acidity, a limited range in saltiness, a limited range in pressures, and a limited range in radiation. And fortunately, we have evolved to control our environment well enough that we can. eliminate most of those factors. Most eukaryotes, those are organisms that have cells like nuclei, like we do. Most eukaryotes are limited to a lower range of environments. But the other two domains of life, they were formerly known as prokaryotes. They don't have a nucleus, they don't have any organelles, they just have cytoplasm, so they just have goo inside the cells. They know no such limits. They can survive in all kinds of environments on Earth's surface and subsurface, with a few exceptions. They can survive at temperatures down to 70 below 0 centigrade Celsius. Now, they don't thrive there and they can't make a living there, but they can live there for a while. And then if you warm them back up to about minus 20, then they can go through their normal life cycles. And they can survive up to temperatures of about 120 degrees Celsius. So boiling water is 100 degrees. So these temperatures are higher than boiling water. They can live in a full range of acidity from values that have a pH, in other words, that's a measure of the acidity, below 1 and even very close to 0, which is just crazy. pH below 1 is not water. It's no longer water. And they can live up to a very high pH value into very alkaline systems, such as around pH 10 or 11. Okay, so 10 or 11, let's see, battery acid is below 1. 10 or 11 is, close to oven cleaner. All right, so they can live under those conditions. They can live in fresh rainwater. There's a lot of bacteria floating around it in the atmosphere. And they can be transported by the atmosphere and rained out all across the globe. Okay? So they can live in very fresh water. But they can also live in brines with salt concentrations many times that of seawater. So this wide range of salty conditions. They can be exposed to very high radiation and still propagate. I don't know if you saw recently the news release about the space station experiments where they exposed some microbial spores outside of the space station. There's a huge amount of radiation coming from the sun. And there's a huge amount of radiation coming from space. And they were able to culture these spores when they got them back into the space station, which is really incredible. And it does speak to concerns about planetary protection. Now, I have to tell you, the champion of radiation tolerance is a microbe called Deinococcus radiodurans. It's known as Conan the bacterium. And it can survive in about 1,000 times the lethal dose for humans. And it can live for short periods of time at 1,000 times that. So it's extremely tolerant of radiation. Now, I want to introduce you to one of the field sites that I have been studying. This is in the Atacama Desert. I had to do that little quick mental check that it wasn't just the Altiplano. It's in the Atacama Desert in Chile. And this site here is at about, must be about 14,000 feet. Okay, so we go up there for several days and do some work there. What you're looking at is a salar. Now, a salar is a dried out lake bed that the water in the lake bed concentrated a lot of salt. Okay, so this basically collected salts that were coming off the Andes and coming in from the oceans and evaporated those off, leaving behind a very concentrated brine that eventually evaporated to the point where we would recognize it as dry. These salars tend to be flat and very large. In some cases, they have small areas of water left in them. But they are not devoid of life. So on the left, you see one of these sites that we studied. Okay, now let's face it. If you walked out there and looked at what's on the left, you'd go, no life there. It just does not look like their life would survive in this kind of environment. It's at 14,000 feet. It's very high radiation, it's very dry, and it's very cold. But if you look on the right-hand side, you'll see, can you see that? There's a little teeny bit of green right there. Here, I'll put my green pointer on it. Little teeny tiny bit of green. So in breaking this piece open, we were able to find a microbial community that can make a living in this system. Now, there's some indication that these types of microbial communities are tens of thousands of years old, so they're not making a great living, but they're still alive. Okay, so let's see, where was I? Now, these organisms that live here would rather live somewhere else. They would rather live in this room. They would rather live in the Clark Fork. They would rather live in the soil. But they've been pushed into these extreme environments because eukaryotes are more efficient at turning sunlight into energy and sugar than they are. So they live where eukaryotes can't. They live where higher plants are not able to live. These organisms, they fit into the bacteria and archaea, two domains of life, formerly known only as the prokaryotes, have DNA and traits that put them on the tree of life, very near the trunk. So the trunk, before the branches come along, is the last common ancestor. And so, say for example, microbes that live in hot springs, they're kind of here. Eukaryotes are way out here in the fingernails. Okay, so thermophiles, they like hot water. They're kind of down here. Acidophiles, halophiles, they are closer to what's called this last common ancestor than are people, for example. We kind of expect that. But these are the kind of organisms that we think, if we're going to find life, we're probably going to find something similar to these. So there's a lot of research into the metabolism, the structure of these microbial communities, how they end up looking when they get into rock, and trying to figure out how they change and how they are preserved over geologic time. Okay. So that's our Earth. Now let's take a look at what else is out there. What other environments are out there that we might find in the solar system that are similar to environments here on Earth? Now, we're not shopping for a Mercedes-Benz. We are going for something very simple, something maybe like a Plymouth. going for all the bells and whistles. Okay, so let's step outside of our realm. Let's go outside the asteroid belt. So we're leaving behind the rocky planets, Earth, Mars, Mercury, Venus, and we are headed out to the gas giants. This is an image of Jupiter. Jupiter has 79 moons. It's amazing. I've found 79. 26 of them still remain unnamed. And the list of the names just goes on and on. Now, Europa was one of the first 4 moons discovered beyond Earth. It's in the company of Io, Ganymede, and Callisto. And all 4 of these moons, as are all other moons, scientific targets for investigation. But Europa is a moon that sparked curiosity because of the possibility that may have hosted or may host life. And the reason for that is because we are able to recognize a very important factor that life here on Earth requires, and that's water. So the initial strategy in the exploration of planets in astrobiology was follow the water. Where was the water? And so Europa came along and had water on it. Now, it's ice. This is Europa out here, by the way. That's its shadow there. It's pretty small compared to Jupiter. Even though it's covered with ice, there's some evidence that there are water bodies below the surface, liquid water, in the form of brines. When first imaged, Europa, Jupiter's moon, showed these unique cracks and unique crack patterns. The cracks in the surface and on the surface were different colors than the surface ice. So they formed by different processes. These cracks possibly formed as substances below this ice sheet oozed up to the surface. Now, why are they orange? Well, we don't really know why they're orange. There are a couple of possibilities. One is that there is a mineral that is in that brine that when it reaches the surface becomes orange. The other is that there are organic compounds in here that are photochemically active, and when the sun hits them, they are turning orange. So there's a couple of possibilities here for why there's this orange system on the surface of Europa. But either way, it becomes an excellent target for life because of the water. All right. Every now and then, Europa releases a plume of water. Now imagine this. Where do we see plumes of water coming out on Earth? Geysers, Yellowstone. So we see these plumes of water coming out in Europa. So that means that it is unstable. And of course, we know the tides from Jupiter wreak havoc on all of its moons. But the fact that there is this constantly changing process, constantly recycling process, makes it a better candidate for life adapting to different environments on this particular moon. Now we're going out to Saturn. Enceladus was not one of the original 4, but it is one of Saturn's moons. It is nonetheless an interesting target. Enceladus is white. It has a covering of clean, fresh ice on it. Again, water. Maybe there's water in the subsurface, maybe there's not. But there is water. It's just in a solid form there on the surface. But every now and then, Enceladus releases plumes of water. Now, these plumes on Enceladus aren't just water. They have organic compounds in them. And so, organic compounds, again, our N equals 1, carbon-based life. So we're very interested in these, and in the process, some of my colleagues are developing instruments that go on drones. They kind of upgrade the drones so that they can fly through plumes and collect the water and the other gases and solids that are in those plumes. Okay? Now, we haven't tried this in Yellowstone because you would never be able to get a permit to do that. Don't try flying drones in Yellowstone. You can't do it. We did try it in Chile. So, and we got some organic compounds in the plume water, which was really a great test of that system. Now, just to cover a couple more of our neighbors, let's look at Ceres. Ceres is a dwarf planet, and it's in the asteroid belt between Mars and Jupiter. In a recent mission to the asteroid belt, the spacecraft Dawn detected complex organic compounds on Ceres. So again, organic compounds are not unique to living systems, but the living systems that we know have organic compounds. So it becomes a good target for, and this is Ceres over here. It becomes a good target for astrobiological exploration. In the lower left, down here, is Saturn's largest moon, Titan. Now, Titan is the only moon that has a significant atmosphere. So we can't really image the surface very well, but what we can see is, through spectroscopy, looking at how molecules absorb and modify light, we see some structures that are in fact liquid lakes. They're lakes. And on Titan, these are hydrocarbon lakes. These are the La Brea tar pits of Titan. Now you would think La Brea tar pits, that's oil. How could organisms live in oil? I mean, water is not very soluble in oil, but it's soluble enough that the water droplets that are found in La Brea tar pits and other hydrocarbon lakes do support microbes. There aren't many, and those water droplets are few and far between, but it is a habitat. It is a habitat that microbes could exploit. All right. Now we're going to talk about sort of what has become the 800-pound gorilla, Mars. So if you look at this quote, I love this quote. It's a fixer-up of a planet, but we could make it work. So that's Elon Musk, CEO of SpaceX, who said those words. We have made the most progress and devoted most of our exploration efforts towards Earth's not-so-perfect twin, Mars. So you'd ask, why is Mars a good target? Well, first, it's close by. It's only 34 million miles away. Venus is closer, so why don't we go to Venus? Well, Venus has a really dense atmosphere. The atmosphere on the surface of Venus has a pressure of 90 atmospheres. So that'd be like hanging out at a kilometer below the ocean's surface. It's a lot of pressure, and it's really hot. So, you know, we keep it in mind, but Mars is a better candidate. Mars is similar enough in size to Earth. It has a very similar composition. They're both made of a rock type called basalt on their surface. So it appears to have started out on a path very similar to Earth, and then took a different route. For example, Mars has no liquid water on its surface today. It does have water. There's a little bit of water in the atmosphere, and there's a lot of ice on the surface of Mars. But there's no liquid water on Mars. Now, there's evidence that there was liquid water on Mars in its earlier days. Now, I kind of slowed down here a little bit because there are some controversies about how much water that was. There are those who think that the water bodies were oceans. There were oceans of water on Mars, which I personally find that really unlikely. Now, maybe there were some crater lakes, kind of like the salars that are in the Andes. Might have been some crater lakes, but more likely water was in a subsurface form. It was there as groundwater, and it came out on the surface and flowed for a while, making streams and fluvial systems and leaving deltas. Okay, and so there's a debate about how much and when water was present on Mars. So when you hear about that, just, you know, take it with a grain of salt. Okay. But there are hydrated minerals on Mars. So if we think about quartz is silicon and 2 oxygens on it. No water at all. If we think about a mineral like that makes up the granite in the Bitterroot, feldspar, no water at all. Those high temperature minerals do not have water in them. But even though we see those similar minerals on Mars, maybe not quartz and maybe not the feldspar in that granite, but we do see those types of minerals that don't have any water in them. We also find minerals that have water in them. They're called hydrated minerals, and we recognize them as clay minerals. Okay, so when you're walking out in eastern Montana and your feet get covered with gumbo, those are clay minerals. Okay, they have a lot of water in them and they store a lot of water, and we know that they're there now. So we know that there must have been more water in Mars's past. We've sent an awful lot of satellites, probes, and landers to Mars. These have, let's see, I think Mars 2020 and ExoMars have not gone yet, but all the rest of these have gone. So ExoMars and Mars 2020 have not gone, but all the rest of these have been deployed to Mars in different places. We've learned a lot of new information about Mars from these, from the landers and from the orbiting satellites. The landers have analyzed the mineralogy, the chemistry, the water content, the magnetism, the grain size, and much, much more, with a suite of instruments that is designed for a specific mission. Okay? And we learn a lot about each of the individual sites. But in a way, we're kind of playing pin the tail on the donkey, blindfolded, and with multi-million to billion-dollar pins. So this shows where we have landed. A very few sites. And so those are the observations we have from the surface of Mars. Most of these are near the equator, and they're near the equator so that they get the maximum solar energy for any instruments that are powered by solar. These sites were all selected from dozens of sites, each with their own scientific proponents and cheering sections. The final selection is based on the goals of the mission. Sometimes the goals of the mission are engineering. So let's take the Pathfinder mission, the one that launched in 96 and landed in 97. That mission was go to Mars, land successfully for less than $150 million. So where they landed was an interesting site scientifically, but would not have been the scientists' first choice. It was the engineers wanted the Sealy Posturepedic landing site so that they could get it there and demonstrate that it was possible. More recently, if we think about Curiosity, which is an amazing engineering feat in itself, had a scientific mission. Its mission was to look at the mineralogy and the topography, to gauge the changes that have taken place on the Earth's surface. The landing site for Mars 2020 has just been chosen. I mean, it was chosen in like November. And that lander on Mars 2020 will go to Jezero Crater. It's a little to the west. Oh, we don't have it up there anymore. It's a little to the west of the Spirit landing site. So site selection's not easy. There were 3 finalists out of many starting candidates. 3 finalists. One of them, Jezero Crater, which is a delta system. Lacustrine means lake, so it's a lake system. You can see here, here's the delta. This would have been a crater lake, so this would have been filled with water, and running off of the highlands into the Jezero Crater would be, oh, you guys can't see that. It makes total sense to me. So the crater is here, as you can see, and this is the delta system that runs down into the crater from the highlands. And here's Jezero Crater in a larger context. The other sites were Northeast Syrtis and Columbia Hills. Now, Columbia Hills may sound familiar to you. Does that sound familiar, Columbia Hills? Gusev Crater. It may sound familiar because that's where Curiosity is right now. So what do? Do you go back to a site you know something about, or do you go somewhere new? It really is a toss-up. Columbia Hills is a hydrothermal and lake target. These images on the left are taken from Gusev Crater on Mars. The images on the right are taken from a hot spring system, El Tatio, in Chile. And there's an amazing morphological resemblance. We know that hydrothermal systems, hot spring systems, host microbes that are very close to the last common ancestor, and that hot springs form these giant white cones around them because the minerals come out of the water. So there's a potential for the microbes to be entombed in these deposits. And here we are. We have something that looks very much like that. And I want to go back. That's where I want to go back. But we're not going back there. So let's keep on with Jezero. So Jezero is this delta lake system. Deltas are really fantastic grab bags. They transport rocks and rock fragments from a large surrounding area and deposit them in a very localized system. As in the deltas on Earth, the delta in Jezero has a high amount of clay in it. These clays are minerals that can easily trap and store organic matter. So this was one of the deciding factors for choosing Jezero. It drained a large area, so there could be lots of different rock types, and we might find organic matter associated with the clays. So that was really kind of it. I'm sure the engineers had something to do with it. The landing will take place down here, which is basically a basalt flat, and then they'll drive over here to look at the area that they're interested in, the delta. This is a mineral map of that area from orbit. This map was built from spectra collected from orbit. Okay, so this information, and along with all the others, fed into choosing this landing site. So when Mars 2020 goes, this is the one. ExoMars is down to 2 candidates. I'm not going to go into that. Now, Mars 2020 is the first mission whose main goal was astrobiology. Its main goal was to search for evidence of life. And it is meant, didn't speak about it in the past tense, hasn't gone yet, it is meant to lay some of the foundation for human exploration of Mars. So that's where we're going. It's going to launch, if everything goes well, in July 2020. And we should be, within a year, on the surface of Mars. Okay, I would like to finish up by saying that these missions answer intriguing questions about life on Earth and elsewhere. They allow us to learn more about ourselves and our surroundings. They lead to new technologies and discoveries, and they fulfill the urge to explore that is in all of our genes. We need to prepare for these missions as thoroughly and completely as we can. So it's a little plug for analogs research. But we will never be able to prepare enough. We will never be able to predict exactly what we will find and where we will find it and what else we have. So I leave you with this quote from Carl Sagan. "The universe is a pretty big place. If it's just us, seems like an awful waste of space." I'll take questions.
Thank you. Any questions? Just raise your hand and we'll bring a microphone to you.
Yes, thank you. I was puzzled at the very start of your talk with the definition of the word organic. What do you mean by organic? You said a meteorite would have carbon compounds on it, but it wouldn't be organic.
Meteorites have organic compounds on them. Let's see, this is over here. Meteorites do have organic compounds on them. So organic compounds are carbon. They're made dominantly of carbon and hydrogen, and the carbons bond together in chains, and the hydrogens bond to the carbons. Those are considered organic carbons. Inorganic carbons, like carbonates, like chalk, for example, are bound to oxygen. They're not bound to hydrogen. So the unique ability of carbon to form these long, long chains is what makes it the building block for life. Did I answer your question?
Okay, another question? Okay, while you're thinking of one, I've got one. When we go to Mars in the 2020 expedition and search for life, how will we know we found it? What are the mechanisms for testing it, and how will you have proof positive if it's there?
So Mars 2020 is a caching mission. And that means that Mars 2020, with its capabilities, is going to choose rocks that have characteristics that we would match what we would expect to find in that type of environment if it were here on Earth. Okay, so that's going to guide the hand that goes out there, or the arm that goes out there and collects that rock. Then it's going to take that rock and it's going to put it in a container. And it will stay there on Mars until SpaceX picks it up. No, I mean, seriously, they're caching it on Mars, and the expectation is that there will be a mission that goes back and gets it. And then it will come to Earth, and it'll probably stay in orbit for a while because of decontamination issues and some preliminary analyses there. But we cannot send the instrumentation that we would need to answer that question to Mars. I mean, one of the instruments that I use would have been like sending a semi-trailer to Mars.
Thank you. That was really some very difficult thoughts explained well. I really appreciate it. In your picture where you show the various missions that went, who is responsible for sponsoring those missions? How do those missions get launched? Is it all NASA, or is it other entities that are working on this too?
Well, originally it was NASA. Of course, it was, early on there were military missions as well, but it was NASA sending the missions into space and off to these other planets and worlds. ESA, the European Space Agency, is involved. The European Space Agency has national contributors to it. So there's the German Space Agency, there's the Astrobiological Center in Spain, there's, I think it's like NRS in France, and they have their own mission, ExoMars, but they also contribute to these missions. Japan is getting in on missions. China is interested in sending its own missions. I am not aware of the level of collaboration with the Russians, but it's become more international. These missions are so expensive that an individual nation just can't afford to do it. Plus, there's all that expertise out in the world, in all the other countries.
My astrobiology is limited to watching The Thing and The Blob, and I'm wondering, those little green guys from the Atacama Desert in Chile, what would happen if you gave them a comfortable home?
It's very interesting that you would ask that, because I have some of them over in my office. And they are definitely more comfortable here than they are in the Atacama, but they haven't taken off. I haven't given them enough water. I mean, they're in their sample bags. One interesting thing that happened, though, we took a lot of samples there, and we brought them back here and started unwrapping them. Now, the samples that look like that, some of them were just put into Ziploc bags. And others were put into foil and wrapped up and, multiple layers and never to see the light of day. We brought them back here, and the ones that were in plastic bags still had their pigments. And the ones that were wrapped up in aluminum foil had already lost their pigments. But exposed them, and they're back. Yeah.
Yeah, my question's along the same lines because you talked about the extremes of temperature, radiation, and everything else. And I've always had this belief that cockroaches, for example, have lived through everything, but they obviously don't. But if they do bring something back from, say, Mars, from what you said about the eukaryotes, or not the eukaryotes, the others.
Eukaryotes,
Yeah.
and prokaryotes. Yeah.
How could you ever decontaminate something that can live through the kinds of radiations, heats, etc., that are not even possible here, so to speak?
Well, there are multiple layers to that. The same problem is addressed when we send a mission to another planet, because are we sending organisms there that are going to contaminate? And the answer is probably yes. I mean, they have specifications for how much they can detect before they'll send it out. But yes, very good question. So there hasn't been a funding call this year, but a planetary protection program that addresses both outgoing contamination and incoming contamination. So there are various things that can be done. Extreme radiation. I mean, they're alive on Mars. They've been exposed to billions of years of radiation, and there's not a reactor on this planet that could irradiate them to that level. So if they survive that, there are things like bleach, but we know that there are organisms that can live in bleach. There are combinations of radiation, metals, and heat that can be used to decontaminate. But again, what we're counting on is that when we get them back to Earth, we put them in these very contained environments where there's less chance that they'll get out.
Nancy, is this on? Okay.
Hi.
You reference, right here, there we go. You reference ice. Has there been any effort to isolate any individual ice crystals and to study their morphology, their crystallography, to compare those crystals with what we have here on Earth?
So that would be the Phoenix mission. And I can't answer that question. I don't know that, but it's very interesting that you mention that, because I was just thinking about that again today. I study the structure of silicon and oxygen, and it's in a mineral or a mineraloid called opal, or in quartz. And water, when it forms the solid, has a structural environment very similar to what's in quartz and opal. And I've often wondered, whether there would be similarities that we could draw between what we find on Earth and the ice there without having to go through the extreme conditions you have to have in order to form all the different polymorphs, or the different forms of ice.
You said that we make quite a few assumptions as we're searching for life on other planets. One of the assumptions was that life is carbon-based. What are the other theories that describe life as not being carbon-based?
What are the other carbon theories that describe life as not being carbon-based? That's sort of a cosmological question that I think about it, but I don't have an answer for you. What do you think? Yeah, yeah, I know Star Trek has popularized that theory. The problem with silicon, even though silicon's atomic structure is similar to carbon's atomic structure, it does not form chains that are long enough to cover all the different structures of organic matter that we would need to have. I mean, I think they can make them now. It used to be like 4 to 6. A soap, a lipid, those lipids that we try and get out of our diet, they have chains of 30 carbons. We can't make silicon chains that are 30 long. There's the structure of the silicon atom just won't allow it.
With all of the data that is collected by all of these different missions to Mars, how is this data distributed? How is it determined who gets to see it and when, and that sort of thing?
It depends on the data. Quite honestly, the funding agencies have a requirement that you share your data either after a certain amount of time or after it's published. Sometimes the certain amount of time gets stretched a little bit. But many of these images came from the NASA JPL site, and there's just a huge library of thousands of images there of the different bodies worlds that we've visited in the solar system. There are some databases where you can retrieve the kind of chemical and mineralogical density measurements, but they are they're not well subscribed. There are a lot of researchers who don't contribute their data or don't format it correctly. And I can give you a couple examples. I can give you an alternative example for a discipline that does do that. So that water science. There are a couple of places to put your water data. One is, the acronym is COASI. I have no idea what it means. COASI, K-U-A-S-I, something like that. And you can put it there, or you can put it in the USGS databases. And there's some effort to make that a higher priority, and it's working. Do you want data?
We have these hydrocarbon lakes on Titan, which we don't attribute to being, if we were to tap the fuel, we couldn't call it fossil fuel because there are no fossils involved, we think. That's I understand it. Meanwhile, we have hydrocarbon lakes on Earth, which we do attribute to fossils. Mm-hmm. Maybe 50 years ago, when astronomer Thomas Gold speculated that maybe there are hydrocarbon lakes, or hydrocarbon reserves, if you want to call them that, on Earth related to non-biological processes. Is there any new information on that hypothesis from 50 years ago? There was some drilling done at the time trying to find hydrocarbons in a place where no geologist would say they should be, and none were found. But that's not a
Boy,
final.
you know, now scientists have the ability to recognize organisms at great depths in the Earth's crust at very, very low porosities, and that those pores are where the microbes live, and they're metabolizing at extremely low rates. So we really haven't found anywhere on Earth that we're absolutely certain doesn't have life in it. It's kind of a disease.
Any other questions? Yep.
We were talking about like finding life on Mars, but we've probably already brought life through previous missions. So like, would it be a possibility with this 2020 mission that we actually find life we've already brought into Mars and we confuse it for life that we think's their life?
Sure, I don't see why not. I mean, Mars, has winds, and they carry a lot of material around the planet. I mean, hopefully that's a very remote possibility, but it has to be considered. I couldn't tell you what the probability of that was.
Great. One more question. Okay. Sunday, we go through the process of changing over daylight savings time. When you come next week, the sun may be up when you come to the lecture next week. So we're going to beat winter yet. I'm pretty sure of it. So we'll look forward to seeing you next week, 7 o'clock. Thank you all.